Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smartyurl.it/Jedi. My advice on how to pass actuarial exams is at smartyurl.it/pass. This video channel is at smartyurl.it/pass actuarial exams. Here's information about online seminars and study manuals for exams P, FM, IFM, and LTAM that I offer. I direct the actuarial program at Illinois State University. You can find information about it at smartyurl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smartyurl.it/help-ISU-actuary. Here's a problem for today for exam P on probability. You are given that the probability density function for the amount of a single loss is f sub x of x equals 0.01 times the quantity 1 minus k plus 0.01 kx times whole quantities multiplied by e to the minus 0.01 x for x greater than 0 and with k being a parameter. If an ordinary deductible of 100 is imposed, the expected payment, given that a payment is made, is 125. Determine the expected payment, given that a payment is made, if the deductible is increased to 200. And here's a solution. So let us first note that the integral from 0 to plus infinity of 0.01 times the quantity 1 minus k plus 0.01 kx times e to the minus 0.0x dx is equal to 1 minus k times the integral from 0 to plus infinity of 0.01 times e to the minus 0.01 x dx. This is actually integral of exponential distribution probability density function with hazard rate of 0.01 plus 0.01 k times the integral from 0 to plus infinity of x times 0.01 e to the minus 0.01 x dx. This integral is actually a mean of exponential random variable with hazard rate of 0.01. So this 1 minus k is multiplied by the integral of a density, which has to be 1, and 0.01 k is multiplied by the expected value of this exponential random variable with hazard rate of 0.01, and the mean is the reciprocal of the hazard rate, so the mean is 100. So this is 1 minus k plus k, so it's equal to 1 for any value of k, so that we cannot figure out the value of k from the standard density condition. Well then, if we have a difficult problem involving expected value, the solution is always to try to use the Darth-Vader rule. So we calculate the survival function of x. That's the integral from x to plus infinity of 0.01 times 1 minus k plus 0.01 k s times e to the minus integral from 0.01 e to the minus 0.01 s ds. Now I changed the variable to s because we're using x as the lower point in the integral calculation. And we use integration by parts in this expression. We take u to be minus 1 minus k plus 0.01 ks, so that du is equal to minus 0.01 k ds, and dv to be minus 0.01 e to the minus 0.01 s ds. So of course you can see that we have u dv in this integral. And then v is equal to e to the minus 0.01 s. And therefore, this is equal to u times v evaluated from s equal to x to s going to plus infinity, minus, but minus minus, because there's a minus in front of 0.01 k ds. So plus k times the integral from x to plus infinity of 0.01 e to the minus 0.01 s ds. This is actually the integral of a density from x to plus infinity, so it's a survival function for exponential random variable with hazard rate of 0.01. So this becomes 1 minus k plus 0.01 kx times e to the minus 0.01 x, because this expression here as s goes to infinity is infinite, and at x we get this value with minus minus, so plus sign in front, and this expression here is simply k times the survival function for this exponential random variable with hazard rate of 0.01. Okay, we combine the like terms, and this becomes 1 plus 0.01 kx times e to the minus 0.01 x. The payment, given that a payment is made with a deductible of d, is x star equal to x minus d, given that x is more than d. The survival function of this random variable is s sub x star of x equal to the probability that x star is more than x, which is the probability that x minus d is more than x, given that x is more than d, which is the probability that x is more than d plus x, given that x is more than d. So it's the survival function evaluated at x plus d. Now, of course, the intersection of the two events, x more than d plus x and x more than d, is just x more than d plus x. So that's why this is the survival function at x plus d over the survival function at d. Okay, we plug in the formulas for the survival function. We just calculated them. And what we end up with is 1 plus 0.01 k times x plus d over 1 plus 0.01 k d times the whole expression e to the minus 0.01 x. The expected value of x minus 100, given that x is more than 100, is the integral of the above with d equal to 100. So we plug in d equal to 100. What do we get? Integral from 0 to plus infinity of 1 plus 0.01 k times x plus 100 over 1 plus 0.01 k times 100. And then we multiply it out, and what do we get? At the top we get 1 plus k plus 0.01 kx, and at the bottom 1 plus k. And the whole thing is multiplied by e to the minus 0.01 x. And that's equal to, well, we factor out 1 over 1 plus k. That's, actually, we split this into two pieces, really. The first piece has 1 plus k over 1 plus k times e to the minus 0.01 x. That's what you see here. And of course, this is the mean of exponential random variable hazard rate of 0.01 because it's the integral of the survival function of that random variable. And then here we have k over 1 plus k times the integral from 0 to plus infinity of x times 0.01 e to the minus 0.01 x dx. This is also mean of exponential random variable with hazard rate of 0.01. Calculated the standard way. That mean, by the way, is 100. This is 100 and this is 100. So this becomes 100 plus 100k over 1 plus k. As this is equal to 125, we conclude that k is 1/3. Therefore, the mean of x minus 200, given that x is more than 200, is the integral from 0 to plus infinity of the survival function, now with k substituted to be 1/3. And so 1 plus 0.01 times 1/3 times x plus 200, that's the 200 that we have here, over 1 plus 0.01 times 1/3 times 200. Okay. So we multiply it out, calculating all this, and what we get is the integral from 0 to plus infinity of 5 plus 0.01 x over 5. You get this from multiplying the top and bottom by 3, so this would make it this guy 3 and this guy 3, but this becomes 2, 200 times 0.01, so that's where 5 comes from, and then 2 from 200 times 0.01 plus the 3 is 5, so, and then what we have left here is 0.01x. Okay, that's equal to the integral from 0 to plus infinity of 1 plus 0.002x times e to the minus 0.01x dx. And then we split this into two integrals. The first one is the integral from 0 to plus infinity of e to the minus 0.01x dx. And that's a mean of exponential random variable with hazard rate of 0.01, which is 100, plus 0.2 times the integral from 0 to plus infinity of x times 0.01 e to the minus 0.01x dx. This is also a mean of exponential with hazard rate of 0.01, so it's also 100. So this becomes 100 plus 0.2 times 100, which is 120, and that's answer A. Please remember this is copyrighted material. The problem itself comes from Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.